Okay, so part two. Let's go back to this problem and go back to the starting starting amounts that we were given. So we were given 2.7 moles of ethylene and 6.3 moles of oxygen. And I think it would be very instructive to step through this reaction 1 mole at a time for ethylene and see what's going on with the rest of the reagents. All right. So let's say you've got these amounts of ethylene and oxygen. You put them together in a reaction vessel and you initiate the reaction. So let's say to begin with that 1 mole of ethylene is reacting. Okay. So I'll put a -1 up here. Okay, so we're depleting our supply of ethylene by 1 mole. And so what's going to happen is we'll then be at a point where we have 1.7 moles left. Now, when 1 mole of ethylene has reacted, how many moles of oxygen had to react? Well, I think you can see from that's where we have to look at the stoichiometry. The mole ratio between these two reagents is 1 to 3. So not just 1 mole, but 3 moles of our initial 6.3 mole supply have been consumed in the reaction. And so then you're down to 3.3. Okay, so that's 3 moles have been depleted, going from step 1 to step 2. Now, in the process, after you've consumed 1 mole of ethylene and therefore 3 moles of oxygen, how many moles of carbon dioxide and water have you just made? So think about that for a second. If you react 1 mole of ethylene, then you must have made 2 moles of carbon dioxide and 2 moles of water. I should put zeros here because at the beginning of the reaction you don't have any of those. Okay, now let's take another step further. Let's say we use another mole of ethylene, and we know that if we're going to react 1 mole of ethylene, that's going to require using up 3 more moles of oxygen. Okay, so after we've reacted another mole of ethylene, now we're down to 0.7 moles of ethylene and 0.3 moles of oxygen. And now we will have added another 2 moles of carbon dioxide, so our total carbon dioxide count goes from 2 to 4. Same thing for water. Okay, so after we've consumed 2 moles of ethylene, we consume 6 moles of oxygen, and in the process we've gotten 4 moles of carbon dioxide and 4 moles of water out of the deal. So I hope this is all kind of making some sense. Okay, so if you were kind of paying attention and getting comfortable with what the mole ratios are, what they really mean in a balanced chemical reaction, then this scenario should make sense. Okay, so now let's draw a line here. So we're at this point in the reaction, you're approaching a critical point, because I think you can, if I ask you the question, at the rate we're going, which one of these 2 reagents are we going to run out of first? Okay, and if you think about it for a few seconds, I think you can see that, we're depleting our oxygen at a rate of 3 moles for every 1 mole of ethylene we're consuming. So we're going to run out of this oxygen first. And if you look at it this way, if we have 0.7 moles of ethylene left, how many moles of oxygen would we need to completely exhaust our supply of ethylene? And the answer is, if you're thinking times 3, okay, you would need 2.1 more moles. And clearly, we do not have that many. We don't have that amount of oxygen left. So we can safely say that the the answer to question 1, oxygen is our limiting reagent. No doubt about it. And then let's see, the answer to the second question. This is where things get interesting. The second question, if you remember, is, let me go back there, how many complete products can we be made? So let's go back here. So let me kind of rephrase the question a little bit. In this context, we could say how many moles of carbon dioxide and water could be formed, right? So number of moles of carbon dioxide and water formed. All right, how many of those could we make? And the strategy here is, since the oxygen is the one that is limiting, then we would base our calculation of, carbon dioxide and water produced on the initial amount that we were given of oxygen. So that's the strategy in these problems, is when you're given the starting amounts for each reagent of a reaction, and you're asked the question, okay, if you were given these amounts, how much of this product could be made? The first thing you have to do is determine which one of those reagents is the limiting reagent. Because once you've determined that, then that is the amount on which you base the calculation to answer the second question. How many moles or how many grams of the product do you need to have? So if we were going to work this problem out, to the finish line, to answer question number 2 here, I guess that's really a question, isn't it? Not really an answer. So the answer to the second question is, okay, so number of moles of carbon dioxide, let's pick carbon dioxide here, equals, we said we would use the starting amount of our limiting reagent, so that's 6.3 moles of oxygen. And now we're being asked for, we're trying to get the number of moles of CO2. This is just a moles to moles stoichiometry problem. And so we need the moles of carbon dioxide, that's 2 moles CO2, and we need the moles of oxygen, that's 3, so 3 moles of oxygen. Because remember, when we set up our mole ratios, we always have to look at the coefficients from our balanced chemical reaction. And let me grab my calculator. When we apply that, 6.3 times 2/3, you get basically 4.2 moles of CO2. And since the mole relationship between carbon dioxide and water in this reaction is 2 to 2 or 1 to 1, we can also say that we're going to make 4.2 moles of water. Okay. All right. So if you kind of followed that, that is it. That is the hardest part of this whole stoichiometry thing. So tell you what, let's do another example just to see if we can get a little more comfortable with this. Sorry about the racket. My wife is running the vacuum cleaner upstairs. Let's say we've got magnesium, and we're going to react that with hydrochloric acid. And guess what? You guys have actually done this reaction. So you know that we get magnesium chloride plus hydrogen gas. Okay, and that is a balanced chemical equation. Let's see. The starting amounts. So the starting amounts that we're given are 5.0 grams of magnesium and 6.0 grams of hydrochloric acid, hydrogen chloride. So notice we are being given the known, the data that we are being given is in mass. And here's a very important point to these limiting reagent problems. If you're given starting amounts in terms of mass, the only way that you can figure out which one is the limiting reagent is to first convert them, and you knew this was coming, into moles. All right, so we need to do a mass to moles conversion real quick, and that's why it's important that these mass to moles conversions be becoming second nature. So when you take the 5 grams and divide by the atomic mass of magnesium, which is 24.3, you should get 0.206. And likewise, when you take the 6 grams of hydrogen chloride and divide by its molar mass, which would be 36.5, you should get 0.164. And these values are in moles. Okay, now this is where we are now in a position to determine which one of these two reagents is the limiting reagent. And so if you look at these two numbers in moles and look at the mole ratio, which is dictated by the stoichiometry, by the balanced chemical equation, you just kind of look at this and you just apply a little bit of common sense in terms of numbers. I think you can see that if you're given 0.206 moles of magnesium, you're going to need twice that many moles of hydrogen chloride in order to completely use this up. And so again, if you're given this much, then you're going to need twice that much, right? Which would be 0.412 moles of hydrogen chloride. And clearly, we don't have that. We're way short on the HCl. So, which one is the limiting reagent? That's the one. Hydrogen chloride is the limiting reagent. And so we're going to then base our calculations on HCl and this amount. Okay, and in the question is asking, let me just write this down. Here's the real question: how many grams of magnesium chloride can be made? Okay, and so we determined that HCl is a limiting reagent, and therefore we will base our stoichiometry calculation on, so I'm going to put an X here, that's what we're looking for. We're going to base it on this amount. Okay, so if you come down here, so number of, or I should just say mass of magnesium chloride equals, okay, the given 6.0 grams of HCl, and then the first thing we do is we multiply that by 1 mole over the 36.5 over the molar mass of HCl. Okay, so that converts the grams into moles. Then we have to make use of the mole ratio between the magnesium chloride and the HCl. So we have 1 mole of magnesium chloride and over 2 moles of HCl, and then finally we have to multiply by the molar mass of magnesium chloride, 95.3 grams over 1 mole magnesium chloride. And when you multiply all this out, okay, so grams of HCl, mole of HCl, moles of HCl, moles of magnesium chloride, moles of magnesium chloride. So good, we've got the units that we want, and it turns out to be 7.81 grams of magnesium chloride. And there we go. So that is the end of part 2. Part 3 is next.